flow over a circular cylinder, you remember that the flow, namely the boundary layer, remains attached on the forward half of the cylinder and then separates on the rear half. This forward half is a region of favorable pressure gradient, while the rear side is a region of adverse pressure gradient. So, we have studied that the boundary layer stays close to the solid surface as long as the pressure gradient is favorable, and will detach from the surface when it becomes adverse. So, the consequence of boundary layer separation is seen in the pressure coefficient, defined as P minus P infinity over half rho u square, where P is measured on the surface of the cylinder. So, this shape is something like this, pi minus theta equal to 0 being point A. This is point A, this is point B, this is point C, this is B, and this is C. This classification of favorable and adverse pressure gradient is carried out with respect to the potential variation. This is the potential flow variation. So, then because the boundary layer remains attached to the surface, the real pressure variation, these are experimental data points, they follow the potential variation on the forward half, and after the flow has separated, that means the boundary layer has lifted off from the surface, pressure tends to become constant. So, these are experimental points. While the solid line is potential theory. Of course, in the previous discussion we had said that flow separation will take place exactly at point C, but that need not be the case. It can be a little around point C. Okay. The reason is the boundary layer. So, you recall the discussion that this is the boundary layer. I am showing it on a solid surface. If you see the velocity distribution, this is the velocity distribution inside the boundary layer. It will take some time before the adverse pressure gradient can stop the flow within the boundary layer and reverse its direction. So, this reversal will happen over a certain distance, which depends on the Reynolds number of the main flow, and therefore, the onset of flow separation will be around point C, not exactly at point C. So, once you have the real pressure variation, you can find drag acting on the cylinder. You remember this expression. Cos theta will give you the component in the flow direction, and this will give you the pressure variation. We have also seen that if you work with the potential variation, this entire solid line. Okay, so, for potential variation, we found the drag coefficient to the drag, which is also drag coefficient, to be 0. But if you substitute the real variation, then the value of C d will work out to be somewhere between 1 to 3, depending on the point of separation. Okay. So, that means depending on whether flow separates a little before pi over 2 or little before pi over 2 or little after pi over 2. So, this depends on this is called the angle of or the point of separation. So, let us go back to this drawing. Let us call this phi s is a point of separation. So, in potential flow, there is no separation. That means, flow remains attached over the surface of the object. So, phi s is pi, right. And in real flow, phi s is closer to pi over 2. So, if you have to find the force acting on this cylinder, that is drag acting on the cylinder, you will break it up into 0 to phi s plus phi s to pi, where here you will set p equal to constant, and here in this part p is potential. What is the potential pressure variation? That is given by C p equal to minus 4 sin square theta. Okay, and what is that constant value? It is the value of pressure at the point of separation. So, this is equal to P r at theta s, that is the value of theta at the point of separation. Okay, and this will turn out to be non-zero, which you can imagine, because on the rear side there is, on this side there is low pressure, on that side there is high pressure, giving rise to a net force acting on the cylinder. So, now you can ask this question, Suppose I want to reduce drag acting on the cylinder. Okay. How can I reduce drag acting on the cylinder? You already have this result if phi s were to be at the rear stagnation point. So, as phi s increases towards pi, C d will decrease to 0. Okay, so, as the point of separation goes towards the rear stagnation point, the pressure variation will be potential for which drag coefficient is 0. So, now the question is how can we make phi s increase towards pi. So, one possibility is to weaken the adverse pressure gradient. So, this process, so what does it mean? See, on the rear side, so this is if I call this A, B and C, A to C is favorable, C to B is adverse. So, there is a variation of pressure from C to B occurring over this angle, but suppose I have to weaken it, I have to, that means the same change will now happen over a longer distance. Okay. That is called weakening the adverse pressure gradient. You have low pressure, high pressure. If it happens over a short distance, the gradient is large. If it happens over a longer distance, the gradient is weaker. So, this is also called the process of streamlining. So, so, you would like to reduce the pressure gradient from C to B by increasing that distance. That is one way of doing it, is to increase this distance like this. Okay, that is shift point B from here to here. So, this is point B prime. Okay, so, now the adverse pressure gradient from C to B prime is smaller than the adverse pressure gradient from C to B. Okay, so, the flow, instead of separating here, this is the boundary layer, it will remain attached and go all the way up to this point and then probably separate. So, now this has become the point of separation. Okay. So, going back to the previous picture, suppose phi s were to be somewhere here, then you know it is going to be a much smaller drag acting on the object. Okay. So, delaying the point of separation by, so this process of delaying the point of separation, weakening the adverse pressure gradient is called streamlining and gives rise to what you may have heard of already. It's an aerofoil kind of a cross section. This is the origin of an aerofoil. An aerofoil cross section has a low drag, mainly because the point of separation is now delayed. by streamlining. This has the main advantage of lowering drag, because potential pressure prevails over a much larger portion of the surface. So, objects for which, so if you have an object with a strong adverse pressure gradient, is often referred as a bluff object, and if the object has a weak adverse pressure gradient, it is said to be streamlined. So, a bluff object is characterized by early separation, a streamlined object is characterized by delayed separation. If there is delay in separation, the drag coefficient goes down. Now, there is one subject we have not studied, which is that this aerofoil shape also has a sharp trailing edge. Unlike a smooth cylinder, you can see that cylinder near point B has a smooth surface, while this aerofoil near point B prime is sharp, it has a sharp trailing edge. This sharp trailing edge is responsible for generation of lift. This point we have not studied, we will see if we can touch upon it later. So, this aerofoil cross section. So, the process of streamlining suggests an aerofoil cross section, for which CD is small and CL is large. By large we mean it is definitely greater than 0. So, that sort of explains the utility of an aerofoil cross section. Okay, so one way of delaying the point of separation is by streamlining. Let us look at one more possibility. So, let us start with a flat plate boundary layer. This is the flow direction. This, what is the second line? That this is the edge of the boundary layer. And is where y is equal to delta, which is a function of x. So, this is the velocity variation. So, as you go downstream along the plate, you can see that the wall shear stress, which is mu u over delta, decreases. Right, because the same variation occurs over a larger distance. Outside the boundary layer, flow is potential. So, there is really no effect of viscosity. All the effect of viscosity is felt only within the boundary layer. Now, some time ago I had referred to the appearance of natural disturbances. That could arise from the free stream, that means this incoming flow may have its own disturbances. If you run a fan, it is going to have its own disturbances. If you think of an object moving in air, air will have atmospheric disturbances. So, there are free stream disturbances. There could be oscillations of the solid surface. So, you may call them vibrations. Surface roughness, these tend to disturb the boundary layer repeatedly, and their influence is damped by viscosity inside the boundary layer. So, the damping capacity of the boundary layer. What is the damping capacity of the boundary layer? So, here you may want to recall again Newton's parallel plate experiment, okay, where you had the surface moving at some velocity u in one direction and the force applied is F. Here also you have a similar situation, the edge of the boundary layer has some velocity. Okay, so, even though it is not uniform opening, that delta changes with distance, but at a given point. So, there is some velocity u. So, the damping capacity, so here we are using an analogy with Newton's parallel plate experiment. So, here in Newton's parallel plate experiment, this is F u. So, the damping provided by the medium contained between the parallel plates is F times u divided by h on a unit volume basis. Okay. Force into velocity, all of it is dissipated in the body of this liquid, F times u divided by h. So, here the damping capacity of the boundary layer will be, what is this F? This is this F is mu u over h a. This is what Newton had proposed. So, here it becomes mu u square over delta square. Okay, this is the damping capacity of the boundary layer, which, and since delta is increasing with x, the damping capacity of the boundary layer sharply decreases with x, with increasing x. Therefore, the external perturbations initially are damped, maybe up to some point here. So, here the damping capacity of the boundary layer is greater than the free stream, these disturbances, and the flow looks very quiet. Okay. So, that state of flow is what we call laminar, but disturbances will persist beyond a certain point. That means, if you put a probe somewhere here, if you put a velocity measuring probe here, it will record disturbances beyond a certain point, and that we call the turbulent state of flow. So, what is the consequence of having turbulent fluctuations in the boundary layer? So, these fluctuations will mix up the fluid. We have discussed how mixing of the fluid tends to make pressure uniform. So, here mixing of the fluid will tend to make the velocity profile uniform. So, in the laminar state of flow, this is laminar, flow is from left to right, and much farther downstream because of the presence of disturbances in velocity, the velocity distribution tends to become flat. Flatter. And this is the turbulent part of the boundary layer. So, now we are in a position to see how the boundary layer over a circular cylinder will react in case the boundary layer were to be turbulent. So, suppose you have an adverse pressure gradient acting on the laminar boundary layer, then it will tend to separate over some distance. So, this is what happens in a laminar boundary layer. So, this might be some distance L1, but if the boundary layer were to be turbulent, can think of it in many different ways. The kinetic energy of the fluid available within the turbulent boundary layer is greater than what you have in the laminar case. You can see that this velocity here near the wall, that is the one that is impacted by the adverse pressure gradient. Velocities here are smaller than the velocities in a turbulent boundary layer, even though you have no slip condition at the wall. So, you can think of this region. It is a region of higher kinetic energy. As a result, there will be flow separation here also, we expect a delay we expect a delay in the point of separation. So, I think I have made a very strong statement. Okay, streamlining. So, just to review the whole thing, if you weaken the adverse pressure gradient, there is a delay in the point of separation. Okay, so that you can do by streamlining. Okay, when you do streamlining, there is a delay in the point of separation and the drag acting on the object goes down. Now, we are talking about a second method. The second method, the boundary layer has been energized, it has been made turbulent. When it becomes turbulent, again there is a delay in the point of separation, because the near wall fluid is a region of higher kinetic energy. So, there is a delay in the point of separation, and there is once again, CD decreases. Okay, so let's see if I can open up. I'm looking for Rahul, can you call Surya? I want my pen drive inserted. There it is. So, you can you recall this graph. This is CD versus RE. The initial part is CD, this is low Reynolds number, where CD decreases with Reynolds number, and then there is a near constancy in CD, and then you see a sudden dip in Reynolds number here to the right, close to 10 raised to 5, 5 times 10 raised to 5. ये काम करेगा? ये वाला. I don't know, can you see the red dot? Yeah, see that red dot, there is a dip in drag coefficient, sudden dip in drag coefficient, which is because of the laminar boundary layer becoming turbulent, resulting in a delay in the point of separation. Okay. So, this point we will take up again. अच्छा, इसको बंद करते हैं, इसको बंद कीजिए. हाँ, ठीक है. अब मेरे अकाउंट, ये इसको खोलिए, या मेरे इसको मैं मेरे अकाउंट में है, पेन ड्राइव में भी है, पेन ड्राइव को डाल दीजिए. हाँ, इसको बंद करता है. ये फ्लो विजुअलाइजेशन ऊपर ऊपर है और ऊपर नहीं ये वाला हाँ ये वाला ठीक है चलो इसको बंद कर दीजिए बंद कर दो हाँ ठीक है हाँ ठीक है हाँ ठीक है और ये कैसे इसी से हैं
राइट करना है सर इस पे क्या
इस पे
जी नहीं
हाँ
राइट करना है सर इस पे पेन से सेट कर लीजिए और ये
बच्चे इस पे लिख सकते हैं हाँ और आगे पीछे
सर ये
हाँ ठीक है पीछे जाइए हाँ ठीक है
वो चाहिए वो
नहीं
सर
ठीक है हाँ ठीक है मैं आ जाऊँगा ठीक है इसको हटाते हैं ये ओके ठीक है ओके सो लेट्स रिव्यू everything we have studied about flow over a circular cylinder. We started with low Reynolds number. So, this is low Reynolds number flow and flow goes around. Flow is in all these pictures, flow is from left to right. So, you have flow going around the cylinder conforming to the shape of the cylinder. You may call it attached flow. Okay. Then Reynolds number increases and you can see you saw the video last time. So, here you have a point of separation. So, please look at the red dot. So, flow is attached up to that point and then there is a circulation bubble. Now, one of the videos sent to you is about the circulation recirculation bubble. That means there is a region of flow separation here. Here flow is from left to right, flow separates, the boundary layer separates and then it happens on both sides and you have a recirculation zone here. With further increase in Reynolds number, by the way, in the experiment, low Reynolds number experiments are carried out in liquids because viscosity is high, it is easy to get low Reynolds number. High Reynolds number experiments are carried out in air because viscosity is already small, easy to generate high Reynolds numbers. So, you can see a disturbed wake here, that's around here is the point of separation, around here is the point of separation and you have this is the disturbed region downstream of the cylinder. This is the far field away from the cylinder above and below which goes around the cylinder. So, close to the cylinder you have a point of separation because of the break in the symmetry between the left side and the right side, there is a force acting on the cylinder. So, let us see. So, this is cylinder and a sphere, they behave in a somewhat analogous manner. So, you can see that here this is a sphere and this is the point of separation. You can see flow separating and this is the disturbed zone. This is the left hand side is an instantaneous picture, the right hand side is a time averaged picture. Instantaneous is just a snapshot, time averages you collect such images for a whole sequence and then average them all out. So, here in the second row, this is the first row, in the second row the boundary layer is tripped to become, trip meaning you introduce a small disturbance and force it to become turbulent. And you see that this point of separation, here it was somewhere there. So, it has now, originally somewhere here, it has now come here, and the disturbed zone here is only this much compared to a much larger disturbed zone for a laminar boundary layer. So, making the flow turbulent delays the point of separation, and just by looking at these pictures you know that there will be a reduction in the force acting on the sphere. So, the same thing happens for a cylinder also. So, which explains in that CD versus RE curve you have a sudden fall in the drag coefficient at a high Reynolds number, which is because of the boundary layer on the surface of the cylinder becoming turbulent, leading to a delay in the point of separation and hence a fall in the drag coefficient. Some small comment on a streamlined object. So, you can see here that this part, the initial part on the left hand side will be a region of favorable pressure gradient. The right hand side is a region of adverse pressure gradient. So, that portion has been elongated. Otherwise, you would form a small cylinder, but by elongating that part and generating an aerofoil cross section, the flow remains attached. So, you can see this disturbed zone on the right hand side is very small compared to the circular cylinder. Okay. So, in a way the size of the disturbed zone downstream of the object is a measure of the force acting on it. Okay. So, you also know that the rate of loss of momentum, you now have to connect it to the global analysis we had carried out, control volume analysis we had carried out. Suppose there had been no change in the velocity distribution, there would be no force acting on it. So, large change in velocity will give rise to a large force acting on it. So, here for a streamlined object, this flow is very similar to the incoming flow. So, the force acting on the object in the flow direction is small. For a circular cylinder, it is large, but if you trip the boundary layer, there is a delay in the point of separation, the disturbed zone becomes smaller, again there is a reduction in the drag coefficient. How much is that reduction? You may want to check up that graph. It goes from some 1.4 to about 0.4, a factor of 3 reduction. It's a huge reduction in the drag coefficient. If you look at drag coefficient of an aerofoil, it might be even smaller, it might be 0.01, 0.02 compared to 1.4 for a circular cylinder. That is 100 times reduction. Okay. But suppose this aerofoil were to be inclined relative to the main flow, then it generates very large zones of disturbance. So, it is no longer streamlined. See, just because you have an aerofoil does not make it automatically streamlined. It has to be aligned with the main flow, then it is streamlined. If you turn it around, it will also become a bluff object like a circular cylinder. Similarly, if you thicken the aerofoil, again the wake size increases. So, your aerofoil, if it is thin and aligned with the flow, it will have a very low drag coefficient, okay, because of the delay in the point of separation. Where is separation here? You can see here that separation is probably somewhere halfway through. Here it is probably somewhere here, near the tip of the aerofoil. Okay, I think this is the shows the same plot. So, if you have a flat plate aligned with the flow, pressure is constant. So, there is no pressure gradient. So, that is like a streamlined object, there is no adverse pressure gradient. But if you hold the plate at right angles to the incoming flow, you can see the disturbed zone is very large. So, it is a highly non-streamlined or a bluff object, and it will generate a huge amount of force acting on it in the flow direction. Now, you can also imagine that the flow downstream of this object is time dependent, which means all the forces are time dependent. Okay, it is not just a large force, it is a large time dependent force. So, this is a small protrusion kept in over a flat plate. Even this small protrusion you can see creates disturbances upstream, downstream, and acts as a bluff object. Okay, these are some videos you have already seen. I think this just emphasizes the same point, that the aerofoil aligned with flow, here flow is from right to left, is streamlined, but if it is at an angle to the main flow, it becomes a bluff object. Okay, these videos of a circular cylinder you have seen already. I think we will just stop here. So, let us so this is flow past a circular cylinder at some intermediate Reynolds number. This is one of the videos sent to you. Where is the cylinder? It is on the left hand side. Flow is from left to right, generating a huge wake. Okay, so I think we touched upon too many points in this